Hey everybody, this is a lecture for week 5 of Intro GIS at UMass Amherst. Stuff that we're talking about today is a lot of topics that are kind of a little bit of review, a little bit of global positioning systems, and things leading up to your exam, which happens next week. So exam next week is going to happen during your lab period. So whichever lab period you're signed up for, that's the lab period that you should come to in Morrill. You're going to have the full lab period, so 3 hours to work on the exam. If you need accommodations, now's the time to reach out to me so that we can get that set up. If you need longer time periods or want to take the exam over in disability services, all of those are totally fine, but we need some time to get it set up. You're going to be taking your exam on the lab computer, so no need to bring your laptops, and because we don't want to deal with any extra problems that might arise associated with Windows virtual desktops. So just plan to come, bring yourselves, bring pen and some paper, and plan to work on one of the lab Windows computers. Extra help hours this week are during regular lab time. So Thursday, Friday this week, and then next week, regular office hours time. So the TA office hours and my office hours are all available to you in terms of helping with exam prep and studying for the exam. What does the exam look like? So a third of the exam is going to be short answer questions. So that's content from lectures and some content from labs. 2/3 of it are going to be practical questions, and those are largely from labs. And by practical questions, what I mean is you're going to, it's not just conceptual, but you're actually going to be opening GIS, downloading some data, and answering questions that we pose to you based on those data. You may bring a cheat sheet. I would really encourage you to put together a cheat sheet. So that can be just a regular 8.5 by 11 piece of paper. You can use both sides. You can write in 6-point font if your eyesight is really good. Whatever you want to put on there is totally fine by me. So make sure you've got that or you've worked on putting that together. There is a practice exam posted in Moodle. So it should be both at the top of Moodle and also in week 5 in Moodle. And it includes things that are generally similar to what you're going to see on the exam. It includes a lot more short answer questions than the number that you're actually going to see on the exam. But if you, on your cheat sheet, work through and make sure you've got the answers to the short answer questions that are in the practice exam, then you should have a pretty straightforward time answering the questions that are in the actual exam. Same thing goes for the practical questions that are in the practice exam. If you can get through those, you've got some pretty good intuition on how to do those, then you should be in good shape for the regular exam. If you are looking for more to work on besides the practice exam, what I would encourage you to do is to go back to your production exercises from labs 1 through 4. Just don't worry about the content going through the entire lab again, but just go to the production, see if you can, now having had a little bit more practice, I think you'll find that you can get through those production exercises a little bit faster than you did the first time. That's the way to study for this exam. Next week in class, so this is the right before the Thursday lab period or the day before the Friday lab periods have the exam. We're going to do a practice session. So that whole class period is entirely for you guys to pose questions of me. At the top of Moodle, there's a Google form, which has basically one question in it, which is, what would you like me to go over? So you're welcome to either fill in that form or bring your questions to class. If I get questions that I can answer, feel equipped to answer early enough in the week. So if you fill out that form, today or tomorrow, so that I can access it by, beginning of next week, then I can also try to post some tutorials on like this one, except an actual GIS tutorial, so that you can refer to those as well. And then, of course, you're also welcome to bring questions to class or ask follow-ups on anything that comes up. All right, so the second piece that we want to talk about is just to go back to the coordinate systems that we talked about last week in week 4. And just a reminder that this is tricky stuff. There's not intuitive, projections and coordinate systems are not intuitive for anybody, so it takes some work. And this is a reminder. First question, you open the source tab for your layer of the world, whatever this is, and you notice down here that it has an unknown coordinate system. So there is no coordinate system, no projection defined for this particular data layer. And the first thing that you want to determine is this a geographic coordinate system or a projected coordinate system? And I'm going to pause so that you can look through the data here and tell me geographic coordinate system or projected coordinate system. All right, so what you should see is when you look at the extent down here, you can see that these numbers are pretty small. They go in a left-right or an east-west direction from -180 to 180. They go in a north-south direction from 83 to almost -90. And given that those are within the -180, 180, -90 to 90, these units are most likely actually what GIS has suggested, decimal degrees. And anytime you have decimal degrees, that is always a geographic coordinate system. So here's a different screen capture, also another data layer of the world with an unknown coordinate system. So here is what GIS has suggested. GIS is suggesting to you that these are degrees. So you should look at these very skeptically as degrees, because these numbers of 6 million to -6 million, -20 million to 20 million are way too big. It's impossible for those to be decimal degrees, because decimal degrees can only go from -180 to 180 and -90 to 90. So you know for sure that these are not degrees. And given that they are not degrees, this cannot be a geographic coordinate system. Therefore, it must be a projected coordinate system. Do we know what these units are? Nope. They could be meters, they could be feet, they could be the length of my pinky finger, whatever. Somebody who defined this projection could have done it in any distance unit that they could define. We would need to look that up. We'd need to go back to wherever we downloaded this layer and figure out from metadata, what the projection is. All we know for sure looking at this is that it is not decimal degrees and therefore is not geographic, must be projected. All right, the next question is, why am I forcing you to do this? Why do we need to spend all this time learning about projections or worrying about this stuff? So there are kind of two main reasons. One is for cartography. From a cartographic perspective, especially if you are displaying large regions like North America or Australia, or if you're describing or mapping the entire world, right? Like all the continents or all of the oceans of the world, that is a point at which projections really start to matter in terms of how your data are conveyed to your audience. Remember, something always gets distorted anytime we do a projection from a globe onto a flat plane. And so you need to make a cartographic choice at some point, and GIS will choose for you, which is not necessarily the choice that you want to make. So the more you learn about projections and the more we think about like, what is it that we want to convey to an audience, the better of a cartographer ultimately you'll be. The other big reason that we need to learn about projections is because occasionally something goes wrong and you need to know that this is one of those things that could go wrong and have a little bit of intuition of ways to troubleshoot things if and when they do go wrong. The good news is that most of the time, if all coordinate systems and projections, as long as they are defined correctly, you can have 50 different coordinate systems in your table of contents, in your map, they'll all overlay just fine. And so there's generally, like hopefully, you'll never have to worry about projections again because everything will be correctly defined and will show up overlapping in the right places. So projections are really only important occasionally when something goes wrong or when I create something wrong and make you guys fix it. That last piece, that GIS can deal with a whole bunch of different coordinate systems, 50 different coordinate systems in the same content. That is because, and this should say ArcPro, ArcMap Desktop, that was also true of ArcMap. ArcGIS can convert between any different coordinate systems, geographic coordinate systems, projective coordinate systems, as long as they are defined and defined correctly. Then GIS has no problem with its sort of internal geography of converting between 1, 2, 3, dozens, 50, hundreds of different coordinate systems and making sure that they align in your map view correctly. So here is a map in which I have 3 different data layers in 3 different coordinate systems. And when I look at that map, which I'm not showing you in the screen capture, but when you look at this map, all of those data are showing up where they're supposed to and aligned with each other the way that they're supposed to. So that's something called on the fly projection, which means that GIS knows how to relate all of these different coordinate systems and get everything into the right place where it should be. All right, then the next thing that I just, back to more coordinate systems projection stuff is to revisit sort of what the datum is, because that is continually a source of confusion. So a reminder that not only is the Earth not flat, so not only is the Earth round, but the Earth is also bumpy and pudgy and a little thick around the middle and has a bunch of high points and low points and stuff on it. We refer to this as the geoid, which just means that this is not a smooth surface. This is the way the Earth actually is, a little lumpy, a little bumpy and pudgy. So what the datum does, this is just a review from last week, the datum takes that lumpy, bumpy Earth and it defines a smooth ellipsoid that is an approximation of the Earth. And that ellipsoid, so an ellipsoid is like an ellipse, except in 3 dimensions, means that it has 2 axes. So one is going to be slightly longer than the other one. And we call these the semi-major axis, the longer one, and the semi-minor axis, the slightly shorter one. What that gives us is this really nice geometry where everything is perfectly smooth along the surface of this ellipsoid. A reminder that there are lots of different datums out there, but the datums are basically built on, go back to that one. If I want this to be an ellipsoid for the entire world, so like the World Geodetic Survey 1984 is a good example of a world-based ellipsoid, then one thing I might consider is, all right, if I want this to go through, I want this surface of this spheroid, the ellipsoid, sorry, to go through the approximate average of all of the topography, lumpy bumpiness of Earth. So one thing that I might do is say, well, along the equator, what is the average, elevation for the equator? And I can take into account, all of the oceans at close to sea level. I can also take into account, well, at the equator, I've got things like Mount Kilimanjaro and some really high areas, some highs and some lows, but a lot of it is ocean, so it might be relatively low. So if I take that number that is maybe slightly above sea level to account for the things like, the continents of Africa and South America, I would get an average number for the entire equator. I might want to make that my semi-major axis distance. So distance between the center of the Earth and the average height of the equator. So that might be if I wanted a world approximation, but let's say I'm in North America instead. So the North America is a continent, right? So by definition, it is mostly above sea level. And we've got some major, mountain ranges like the Rockies and the Appalachians to deal with, where, a ways further above sea level than the equator might be, since the equator encompasses a lot of ocean. And so if we want our ellipsoid for North America to go on average through the center of the North America, or through the height of the North American continent, then I might choose my semi-major axis to be a little bit further away than what I would choose if I were trying to approximate the entire Earth on average, because for North America, I'm trying to get to a continent that's a little bit further above sea level than the equator. So those are reasons why different datums exist. But relative to the distance between the center of the Earth and the equator, that difference between sea level and a couple hundred meters above sea level is pretty small. So it's a minor adjustment that adds precision, but it's still pretty small relative to the 6,000 kilometer distance from the center of the Earth to the edge of the Earth. So if you choose a different datum, if you say, I want to use North American datum as opposed to the World Geodetic Survey, those are going to put you in slightly different locations. But this is 500 meters, so the difference between those two things might be a couple of meters, not a couple of kilometers, kind of thing. So the different datums, if you misdefine, if you tell your geographic coordinate system that I'm using WGS 84 when it should have been NAD 27, it might put you off by a few meters. And then back to the steps in the map projection process, right? So we just talked about using the datum to go from the geoid, the lumpy bumpy Earth, into the reference ellipsoid, so this smooth surface. I didn't talk about this last week, but just so that you know, there is actually another step in here, which is that we take this ellipsoid and make it into a perfect sphere. So the perfect sphere, again, is this approximation of the Earth before we go into the actual projection process. You can stop at this point with the reference ellipsoid and just deal with the Earth in terms of angular units, in terms of decimal degrees. You're done. That's a geographic coordinate system. Or you can say, I need to get this information onto a flat surface. I don't want to just deal with angular units. I need some distance units because I want to be able to measure distance. I want to be able to measure area. And that's where you choose a projection on top of this smooth surface, and you go to either a flat map, like an azimuthal, where the piece of paper intersects, like one hemisphere type of thing of your Earth. You can wrap your cone around the top of your Earth, right? So that it intersects mainly at a line of latitude. That minimizes the distortion along the line of latitude. Or you can wrap a cylinder. wrap a cylinder either this way, minimizing distortion around the equator, that's the Mercator projection, or you can wrap a cylinder sideways along a line of longitude, minimizing distortion along north-south along that line of longitude. That's the transverse Mercator. So those are some of the common ones, just as a refresher from last week. Why are there so many different projections and not just those? So, this is a cylindrical projection, but these ones are very much not. This is the Earth as a cube, basically unfolded into 6 different sections. This is one of those Earth as a peeled apart feature. This projection, in fact, is focused on the oceans. So that's why you have these sort of like splits in the continents as opposed to splits in the oceans that we're used to looking at. So why do we have so many different projections? Those are all for different cartographic choices, right? Depending on what it is you want to display, depending on what you want in the center of your map versus on the edges of your map, depending on whether you want to focus on the oceans versus focusing on the continents, whether you want in equal area, like this one type of projection, I think this is equal area too, versus, some other similar shape or similar direction. All of those are cartographic choices, depending on what you want to show people. All right, so the rest of this lecture, before we get to some tutorials, which I'm going to record separately, the rest of this lecture is about global positioning systems. So the question is, how do we know where we are, where you are? One of the ways that we know where we are is using GPS. So back in the day, before we had satellites, how did we know where we were? Well, there were some really fancy ways of measuring location based on the stars, based on sextants, so we could measure the horizon relative to celestial bodies that we knew where they were supposed to be, and try to use that information to figure out, where we are on Earth with some pretty good precision. And that was really important if you were in the middle of the ocean, someplace trying to get from one place to another without the advantage of modern technology. Another way that we can figure out sort of where we are is what's called dead reckoning, which is basically where you have a compass and you have a speedometer, basically. So you have a direction and a speed, and then you can figure out, okay, after this much time, I will have gone this much distance, and figure out exactly where you are compared to where you started. More modern, although these pictures are a little old, I'm noticing at this point, but more modern is global positioning systems. So these are things that many of you have probably seen sort of built into your cars, or maybe at some point you had a Garmin or have a Garmin to go on hikes to get you from point A to point B. This picture on the left is one that you might have seen something similar in terms of surveying. So occasionally, around Amherst, we'll see surveyors from the Department of Transportation out on the roads, trying to figure out, okay, exactly, where is this road supposed to be? Like, what is the slope of this road with really high precision, so that they can, so that they can figure out if that is good for our driving and stuff like that. So where does that information come from, right? So we have this little gadget that we can look at. GPS is basically because we have a bunch of satellites that are in orbit around the Earth. And those satellites know a couple of things. They know with high degree of precision exactly what their altitude is. So how high up they are around the Earth. And they also are constantly broadcasting a signal back to the Earth. And so then you can, from your little digital display, what you are measuring is essentially for a whole bunch of different satellites that my handheld device is able to communicate with, how long is it taking for my message for something bounce from the satellite to my garment and then back to the satellite? How long does it take for that message to transmit? And if we know, how fast that message is going and how far away the satellite is, then we essentially have a sphere around each of these satellites that describes all of the possibilities of where you could be, right? So if it's just around one satellite, then you could be in space, you could be on Earth. There's a lot of different possibilities of like areas where you could be. But as you start adding more and more satellites to that, you hone in on, okay, there's actually only one spot where all of these satellites are overlapping. And that is on my fancy tractor in my super fancy field with all of these different colors. What's the history of global positioning systems? So it is actually, I don't know, I guess it's a while ago, but it's not super recent that the first GPS systems were launched. So 1978 was when the first satellites were launched. For the first 5 years, all of those satellites were kept, they were military secret. In 1983, that changed. So it went from military technology to civilian technology. And then by 1995, they had launched enough successful satellites in orbit that they could mostly see like the entirety of the Earth. And this graph, but yeah, only goes until this continues. So there are more in orbit today than what's happened since 2011 or thereabouts. Which means that, if you've got dozens of satellites, GPS satellites in orbit, then from pretty much anywhere on Earth, your Garmin can communicate with multiple different satellites and therefore, with pretty high precision, identify where you are on Earth. This changed from the original satellites launched for military uses only and into civilian technology was actually caused by a tragedy that happened in 1983. So there was a Korean Airlines flight. So this is before planes had GPS installed on them. There was a Korean Airlines flight that was flying from Anchorage to Seoul, and it got off track because it didn't have any kind of GPS on it, and it meandered into Soviet airspace. So this is 1983. So at that point, Soviet airspace, and it was shot down and killed everybody on board. And so at that point, President Reagan said, all right, we need to make sure that this technology is now available to civilians and to private use because we have the technology to ensure that this doesn't happen. Although the military still didn't make GPS sort of easily usable by the general public for another couple of decades. So what they did was, even though they made it so that this type of error would never happen again, but they still scrambled the signals a little bit such that you would get a error of tens or more meters away from where you actually were. That lasted until 2000, when President Clinton at that point said, all right, no more scrambling of GPS signals. And from then on out, we've had pretty high precision. You can see, so this is the pre-scramble. This is when it was scrambling, and you see a lot of error in terms of distance, both vertical and horizontal. And then after that, it smoothed out to be within, a couple of meters, as opposed to tens of meters. And so that means that when you're driving in your car GPS can generally put you on the road that you're on, as opposed to, a couple of roads over, which would have, if there were GPS in cars prior to 2000, that's what would have happened. All right, and so what are some GPS applications? So these are all pictures of animals with GPS radio collars of one sort or another, where, you know, in the larger animals cases, like the cows, sheep, elephants, these are actually collars with GPS units on them. They are communicating with those satellites and recording the information where these animals have moved. Smaller critters like the geese or whatever that thing is, they are often not GPS, not like recording real time to the satellite. Some of them might be, but they also sometimes have other forms of like things that they go by, you know, like in set up in the field. So they do that with fish, for example, when you're underwater. If a fish swims through a transmitter, then if you've got a transmitter attached to it, it'll ping those locations. But these days they've done amazing work, you know, especially with birds, because you want to be really careful not to put anything that's going to be heavy enough to weigh down a bird so that it would actually injure that animal. They've done some amazing work with really lightweight radio collars or tags that they can put on different critters to figure out what their migratory routes look like, where they're crossing roads, what their ideal habitat looks like, where they're spending a lot of time. Those are really important pieces of information that we need to know if we're doing conservation, restoration, thinking about recreation activities, thinking about where we're going to put new roads in ways that are minimizing harm to wildlife. Another GPS application that you guys might be familiar with is precision agriculture. So this is one where we've talked about Mike's maze up in Sunderland, right? So if you want to create a corn maze, precision agriculture would be a good way to do that, where in this case, you can actually program into the computer the exact path that you want your tractor to take, and then drive it with the assistance of that computer. Not only does that allow you to make a corn maze if you wanted to, but it also minimizes sort of the back and forth of, you know, sowing your field. You don't have to repeat some areas, you're not going to miss some areas, and that's much more efficient. And especially for a lot of farming that's like right on the edge of successful and unsuccessful in terms of costs, having that, making sure that everything is fully planted is optimal. Another use of precision GPS is in terms of earthquake monitoring. So one thing that geologists do is they have these types of precision GPS units set up along fault lines. And before earthquakes happen, or during earthquakes, or after earthquakes happen, sometimes the earth is buckling a little bit or starting to slip very slightly or change its morphology. And so precision GPS can pick that type of thing up, right? It can actually see centimeters, maybe even millimeters of change in the Earth's surface. And so if you start to see that kind of movement, it can give you a little bit of advance warning of this is a fault line that is likely to slip sometime soon, potentially causing an earthquake. It's also something that geologists use a lot in terms of monitoring volcanoes. So if you want to know if a volcano is likely to erupt soon, paying attention to whether the edges of that volcano are changing, you know, rapidly or staying about the same can give you advanced warning on volcanic eruptions. And then another GPS application in terms of buildings is a lot of really tall buildings, really large bridges have GPS units installed on them, so that the folks who want to make sure that all of these, you know, buildings and bridges are robust and are not going to fall down, so that those folks can monitor, okay, there's a hurricane that comes through, like how much is my bridge swaying back and forth? Is that still within the specifications that this bridge was built for? Or, you know, if it's outside of that, that's a red flag. We need to go check out and make sure that that these buildings, these bridges are going to stay stable. And then one last GPS application, which if we're doing the scavenger hunt this week, this would be relevant to the scavenger hunt. Snow affects the scavenger hunt though. So if you're, this week for watching this, there is not going to be a scavenger hunt, unfortunately. So check your, I made that announcement on Moodle earlier. This is not 2022 when you're watching this, then check Moodle for the GPS scavenger hunt information. There are lots of geocaches around. So this is a thing that lots of people do where they hide, oftentimes like a stamp or a sticker or something like that, someplace, and then have information posted on the internet on, latitude, longitude of wherever that cache is. So you can go for your own treasure hunts for geocaches if you have a GPS unit to do it. All right, so I'm going to stop talking there. And basically from here on out, so I'm going to post also a little walkthrough tutorial just as a reminder on selections, and then another walkthrough tutorial that is a reminder of when to use selections versus when to use geoprocessing. So those clips and erases and stuff like that. So I'll post those when I get to them below this recording, but keep an eye on those. Those will be helpful, I think, as exam prep as well. All right, thanks very much.